Back for another day. Sorry about yesterday. The video had no audio for some reason, so I don't know what happened there, but I know now this one has audio, so that's good. But yeah, I think we're at episode 26 now. To be honest, didn't even think we'd ever make it at episode 26, but we have. So let's do our Pokemon of the day. We got Raichu. Let's do Raichu sound. Nice. Good sounds. Right. Nice. Okay. Anyway. Where we ended yesterday was at this problem. We never exactly finished, but we were getting close. Till my friends came and kind of, interrupted. But yeah, we're going to continue working on this one. And then we might take a look at the problem of the day, I think. See kind of what it is. Maybe it might be a good problem to check out. Let's just check it now. Oh man, I hate ones like this. Okay, maybe not, but we might take a look. We'll see. We'll finish this one first. Let's figure out what we're doing here again. So, looping right. If it's in the dictionary, we update our max length. We update our left pointer. We add a new right. Time max length. Okay, what we're going to do here, given a string, find the length of the longest substring without repeating characters. Longest substring without repeating characters. We definitely need to fix this if statement, because if we see that it's repeating, we're only moving up one to the right, so we're not actually removing that W. So yeah, we definitely need a while loop here to get us to here. If S is in my dictionary, do while we need a while loop here to catch us up, so I think we can just do this, like while S right. We update our max. And next out of range. No, that's not going to work. We check if it's in the dictionary. If it is, then we use a while loop while trying to think how we can do this here. First of all, we need to update before I think we go into this while. We got to update our max length. Actually, yeah, copy and paste this. And then we're gonna edit ourselves. I honestly just, I know there's an issue here. I need to make this a while, but okay, if swrite is in my dictionary and my underscore dictionary, that's right, greater than or equal to left. The character's in the dictionary and its index is within the current window. I'm gonna move our left pointer to the right. That's not moving our left pointer though. Okay, we're moving the left pointer, so we're not doing this, right? We're actually moving it to the right of the last occurrence. So we would do underscore dic s right plus or equal what's this equal to my dictionary s right equal to 1, right? Yes. And we're updating our max length. We already updated our left pointer, so we don't need that. We need to add a new right. Alright, so let's run return max length. This is used, so we've got an issue with this here, with duplicates. When you encounter a character that has been seen before, might tell you that the last index where it appeared. Here, my guess right is equal to right. Okay, so for right in range link if it's in the dictionary, if sRight is in my dictionary and my dictionary sRight is greater than or equal to left, then we move our left pointer. Our left pointer is equal to my right s plus 1, so we skip the duplicate. Add new right. Update. Chars C index. Okay, so we're updating the actual index. Yeah, last seen index. Okay. We weren't solving using indexes last time, but let's see how we solved it last time. November 12th. Oh wow, we used just a hash set. Right arranged like this. Oh, that's right in hashy. Hashy to remove s left. I didn't even think about that. Could totally just use a hash set because it's repeating. It's a keyword. Man, I didn't think about that. Okay. Alright, cool. Let's take a look at some patterns. Dude, we gotta stop pumping through these backtracking ones, bro. Like, check out subsets. I think we've done this problem before. No, we haven't. Given an integer norms of unique knowledge, general plus subset the power set. This power set must not contain duplicate subsets. Return the solution in any order. Interesting problem. I think we could do this pretty easily, iteratively. But to do this using backtracking, dude, I don't know. I don't know what it is, but like every time I'm using backtracking, it's just so hard for me to like think about the solution. Like it's like the most difficult thing for me. Like I don't understand why, but I know what, I know. Oh my gosh, I know what backtracking is. It's just so hard for me to implement dynamic programming, backtracking, whatever. Like, it's sorry that I just realized that this is in the way. My bad, guys. Oh, it's alright. You guys are still seeing it, so it's okay. Okay, anyway, let's check this. Sorry, we got ignored by text.
Solve the problem subset. So we're given an integer array nums, and all we need to do is return every single possible subset that we could create from the input nums. And we do not want to include any duplicate subsets. So what is a subset? Well, let's say we have 1, 2, 3 as our input. One subset, of course, would be 1, right, by itself. Another subset would be 2 by itself. We could do 1, 2 together, Now, what happens if we do 2, 1, right? We just swap the order. Does that count as a different subset, or is that the same as this subset? Well, they're the exact same. We don't care about the order. This is not a permutation. This is a subset. So it's not a permutation, it's a subset. So we do not want to include duplicates, and this counts as a duplicate. We're not going to include it. And 3 is another subset. 1, 3, 2, 3, 1, 2, 3. The original input is technically also a subset. And we also don't want to forget the empty subset. So no matter what we're given, an empty subset is technically a subset of this as well. So if we want to create all the subsets from this input, we have a choice for every single element. So for this 1, we have a choice of include the 1 in our subset or not include the 1, so we get an empty subset, right? So we have that choice, and we have that choice for every single input element. So in total, we have 2 choices here, 2 choices here, and 2 choices here. So this is going to be 8, or in other words, 2 to the power of n, where n is the size of our input, right? So this is the number of subsets, and we don't want the number of subsets. We actually want the subsets themselves. So how long could a subset be, right? Well, we could have a subset 1, 2, 3, right? The size of our input. We could also have subsets that are smaller, right? Like 1, 2, maybe 2, 3. So as you can tell, this is not going to be an efficient problem to solve. We have this many subsets, and each subset could be up to length n. So the worst case time complexity of this problem is going to be n times 2 to the n, regardless of how efficient we make it. Because given the constraints of this problem, we don't want the number of subsets, we want the subsets themselves. We have to make it inefficient. So with this in mind, we can just jump straight into backtracking, which is the brute force way of solving this problem, but it's also pretty much the most efficient way. So like I said, for each of these elements, we have a choice. So I'm going to draw the decision tree. So first, we can choose to add 1 or not add 1, and that will give us 2 subsets, 1 subset with just 1 and 1 empty subset. So along this path, we can decide now, do we want to add 2 or not add 2? So with one decision, we will add 2, and the other decision, we won't add 2. So we'll get 1, 2 as 1 subset, and the other subset will just be 1 by itself. And we can actually repeat that on the right subtree for 2. So we can decide to add 2 to this empty subset, or we can decide to not add 2 to the empty subset, in which case we'll get a subset with 2 by itself, or we'll get the empty subset again, right? This is where we're just not adding anything. And lastly, we can decide whether we want to add this 3 or not. So if we add the 3 to this subset, we'll get 1, 2, 3. If we don't add the 3, then we will remain as 1, 2. And we can repeat that decision over here, and that's basically what I'm going to do now, right? Repeat that decision for every single one of our, like, you can call them nodes or you can call them leaf nodes. That's just what we're doing. So if I add the 3 here, we'll have a 1, 3. If I do not add the 3 here, we'll have the 1 by itself. So you can kind of see these are 4 unique subsets, right? Now let's build the rest of the 4 from over here. So I have the choice, do I add 3 or do I not add 3 to this subset? If I do, I will get 2, 3. If I don't, I will have 2 by itself. And you can see these 2 subsets are different from the subsets over here. These are still unique. And lastly, we can choose to add 3 to the empty subset, or we can choose not to add 3 to the empty subset, in which case we'll get a single empty subset. Now you can see we keep multiplying by 2, right? So here we had 1, we multiply by 2, now we have 2 subsets over here, right? We go down again, we multiply by 2, now we have 4 subsets over here, right? Then we go down one more time, multiply by 2, we have 8 subsets, and they're all unique. This is our result. This is what we're building with this problem. This is backtracking. Now, if you want to know how to do this backtracking solution in code, let me show you right now. So So let's do this with backtracking. So we're going to have a result list, which we're going to add these subsets to. And I'm going to do this with backtracking depth first search. And I'm going to write this function inside of this function so that we don't have to pass in this variable or this variable into it. We'll just have access to it by default. But I'm going to pass in I, which is the index of the value that we are making the decision on. So we had 1, 2, 3. So initially I'm going to pass in index 0 for this one. And, this will be index 1. This will be index 2. That's going to tell us whether we decide to add 3 or not add 3. So this I will tell us which element we're currently visiting. And so we know that the base case for this will be if I happens to be out of bounds. So if it's greater than or equal to the length of our input, we know we're out of bounds. And in that case, we can just return. Now, what data structure am I going to use to build each subset? I'm going to have an array, and I'm going to allocate it outside of the function so that we have global access to it inside of this function, right? So let's say let's actually call it subset. Let's say that it has the subset that we currently have. If we ever reach the base case, we know we've gotten past our leap node. So what we can do is add that to our result. And I'm also going to add a copy of the subset because the way it works in Python and in most languages, this subset is going to be modified, right? So we know we have two decisions. So this is the decision to include nums of I. So this is like our left decision that I showed you in the picture, right? So what I'm going to do is to the subset, I'm going to append nums of I. And then I'm going to recursively run depth first search on the next element, so I plus 1. So this is going to be like the left branch of our decision tree, and this is going to be the decision not to include nums of I. So basically we're skipping nums of I. So how am I going to do that? I'm going to take the subset and just pop the element that we just appended. And then I'm going to recursively run depth first search. I'm basically going to do the same thing. So these two function calls, while they look the exact same, they're going to behave slightly differently because for this recursive call, it's going to have a different subset given to it. And this recursive call is going to have an empty subset given to it. So now the only thing left for us to do is call our function. Of course, we're going to pass an index 0. That's the first value. And then we can return our result. So as you can see, it is an efficient solution. Luckily for us, the order that we have
Oh my gosh, dude. Oh my gosh. Alright, I'll be back. 1 second. What up, guys? We're back. Sorry. I had to do a few things. As you can see, it's dark outside, so I actually took a nap as well. So I was actually very tired. So anyway, we're back at it. We're gonna continue with this video, and I kind of took a little bit of a read of this, kind of off camera a little bit. It's kind of helped me kind of think about it a little bit, how the recursion works. Again, I think I just need hella practice on these. I think it's probably the most important thing for me to grow and to understand this. So I'm going to kind of attempt it, the backtracking version. So I know obviously we need our result array. We need our current. Okay. Now we're going to need our recursive function. DFS. We pass in I, which is the index of where we're currently at. We want to check out of bounds, right? So if I is greater than or equal to the length of nums, then we just want to return Turnco. I assume, right? Then, with the way that I think about it, we will need to take two separate calls. So we need to include one that adds, and then include one that pops, right? So here for the one that adds, okay. Sorry. Okay, I'm not really too sure.
Add that to our result, and I'm also going to add a copy of the subset because the way it works in Python and in most languages, this subset is going to be modified, right? So we know we have two decisions. So this is the decision to include nums of I. So this is like our left decision that I showed you in the picture, right? So what I'm going to do is to the subset, I'm going to append nums of I. And then I'm going to recursively run depth first search on the next element, so I plus 1. So this is going to be like the left branch of our decision tree, and this is going to be the decision not to include nums of I. So basically we're skipping nums of I. So how am I going to do that? I'm going to take the subset and just pop the element that we just appended. And then I'm going to recursively run depth first search. I'm basically going to do the same thing. So these two function calls, while they look the exact same, they're going to behave slightly differently, because for this recursive call, it's going to have a different subset given to it. And this recursive call is going to have an empty subset given to it. So now the only thing left for us to do is call our function. Of course, we're going to pass an index 0. That's the first value. And then we can return our result. So as you can see, is an efficient solution. Luckily for us, the order that we have our subsets in the result doesn't matter. So for example, if we had an empty subset and we had 1, that's the same as if we returned 1 and the
Okay, we're gonna do, I think it's res.append current.copy, right? Subset, yeah, that's what, yeah, okay. I don't think this matters. Here we're gonna call our DFS on I+1. And then we gotta append I res, sorry, current.append nums I. And we do current.pop. Oh, we don't need to do anything there. And we do DFS I. Alright, DFS I+1 still. Subset though. Obviously want to call DFS 0. DFS 0, and we want to return a res. Okay. I'm going to make sure I understand it. I'm going to do a paint, right? Okay. Probably going to be a pretty big paint, not going to lie. I don't know how the hell I'm going to do this, but let's just do this. Okay, so we start off with, so our res here. Make it a little bigger. We have our res, we have our current, right? So we start with DFS 0. So we're going to check for inbounds, so we are inbounds. We're looking at 0. So we skip this. We append nums I. Okay, so we append to current nums I. 0. Or DFS 0. That's actually, sorry. We're gonna do 1, 2, 3. I guess we'll write it up here. 1, 2, 3. Okay. Oh. So we'll append 1. So our cur has 1. Then we're gonna go in here. We're gonna append nums I, which is 1, and then we're gonna run our DFS I+1. So we're gonna go to 2, right? So then I think we're going to run through 2, because then say this gets called, so we're going to run through 2 again. So we're going to go to 2 here. So as I is greater than or equal to 2. No, it's not. So we're going to append 2. Right? Then we're going to run DFS I+1 again on that one. So DFS I+1, we're going to go to this, skip this, we're going to go 3. So then we're going to append 1, 2, 3, right? So this is going to see that it's equal to the length. We're going to append 1, 2, 3 here, right? I wish you could make this bigger on here, bro. Like, now I think we're going to go, so we called this one, we went here, went to the length, so we returned. So then I think we go back to the other one, we do DFS I+1. Right, so then we're looking at 2 again, right? I think. Oh, we do code.pop, sorry. Okay, we do code.pop. So this brings us back. Then we do I+1, so we go back to 1. So then 1 is in here. right? Then we go into here. We append. We have 2, right? We append 2. I plus 1. 2 is less than 3. I'm confused here. Oh, the third call returns. Nums2 is removed from the subset, which is now 1, 2. A new call is made for DFS3. Okay, DFS3 goes back. 5th call, DFS3. 2nd call returns nums1 is removed from the subset, which is now 1. A new call is made to DFS2. The 6th call, conditioner. DFS3, the 7th call. Man, this is tough to think about, bro. I don't understand how people like think about this. Like when they're writing this code, I don't understand how they're like visualizing this in their head. Like I really don't fucking get it, to be honest. Like it's generally really impressive because I would never think about this. Like, you know, it's very impressive. Like, but I understand, so we're gonna submit it. I'm going to go to our next problem, subsets 2. So look at a little bit like how to get better at backtracking problems right. And Queen's problem, dude. I remember learning this in college, like, let's jump into an easy backtracking problem. Trying to think, like, let's tag backtracking. I want to get better with these, man. Like, backtrack. We'll tag. Can we tag easy? Maybe they're not tagged medium. Just did the ones with the highest acceptance rate. Subsets was one of them. Damn. All paths from source to target. Let's look at this one. No, these are graph ones. I don't want to do graph ones. I have to get the graph ones. I still haven't really looked at that yet. No graph ones for now. Let's check out this one. What's this one? Okay, this one looks like an all backtracking one. Okay. You're given a positive integer n. A binary string x is a valid if all substrings of x length 2 contain at least 1, 1. Return all valid strings of length n in any order. N is equal to 3. You're given a positive integer n. A binary string x is valid if all substrings of x of length 2 contain at least... I don't understand. What the hell is this? Code roadmap, dude. I think we should follow back to some of these problems. Like, pretty good with these 2 pointers. I gotta probably relook at some stack ones actually, but so length 3. The valid strings of length 3 are oh, okay. I understand here. So we're doing n is equal to 3. We're doing all the valid combinations of n is equal to 3 in binary, so just 1s and 0s. Okay. That makes a little bit more sense. Okay. Let's try and think of this like in terms of a backtracking, in terms of a tree kind of sort of thing. Where we begin, we got 0. So let's do n is equal to 3. N is equal to 3. So we have 0. We go 1. Oh, I don't need a fucking circle. Like, any binary string x is valid if all substrings of x of length 2 contain at least 1, 1. I think it would be kind of similar to the other one, no? Like, you would think, like, what, 0, 1. You could have 0, 1, 0. Sorry. Zero, 1, 1. Backtrack back, have 1. This is totally wrong, this tree, I already know, but I have no idea what I'm doing. I'm just trying to kind of think of the ways to do it. 1, 0. Or there's 1, 1. Or there's 1, 0, 1. 1 0 0. 1 1 1 1 1 0. Where's 100? They don't have 100. How is 100 not one on them? Yeah, we have our res probably similar. We have a current. Okay. Yes, if our length, if the length of of x is equal to 3, then we want to cur.append res.append cur.copy. Okay, we have two decisions. All right, we do our one decision. We do cur.append current.append 1. Then we update our recursive call. We do I plus 1. This is definitely wrong, but you know what, like, screw it. Like, at least we're kind of thinking about it in a way. Sorry, we want to do cur.pop. I know this is so wrong. I don't even want to keep typing it because I know it's so wrong. Recursive I plus 1. Return res. length of current. Let's take a look here. Oh shit, that's... I is equal to n. That's our base case. That's kind of what I knew what the base case was. Okay. Apple 11111. Actually, we're actually kind of doing something. Length, okay, current is equal to n. Result append current. What is current? It's current. Current's I actually. With aggressive current plus 1. Number 2. 0. Only if the last character is not 0. Curveball. Oops. Cursive. What's this? Bro, how did I not see that, bro? These. So we add 1. Add 0 if the last character is not 0. So if not I. So pretty much if not I, if I is empty, right? Let's make sure. This checks if the string I is empty. An empty string values to false in Python, so not I will be true if I is empty. Right. Okay, if the last character I is not 0. This is interesting. I like this problem. This is a good problem. Obviously here it's starting with an empty string, right? Okay. You can either add 1 or... Okay, so... Who do I call? We would call in 0, 0. So we're going to start with an empty. So then we're going to put in 1, right? And then we're going to say well, if I is not empty, if I is empty, it's not empty, or if I minus 1 does not equal 0, then we can add a 0. So either we can go, from here we can go 1, 1, or we can go 1, 0. Right, but here we're gonna go add 1, 1. And here we're gonna go 1, 1, 1. And then here we're gonna go, because we're gonna go back to this one, we're gonna go 1, 1, 0. Right? So this will be number 1 here. This will be number 2. Then we're gonna go back. We're gonna go back to 1, 1. Right? Wait. Okay, so we finished here. We're gonna go back here. We're at 1 here. We're gonna do the 1, 0. We've got a 0. So then here, we only have one choice considering this does not equal 0. So we're gonna go back here. We're gonna go down here. We're gonna go 1, 1. Sorry, 1, 0, 1. My bad. What am I doing? 1, 1, 1, 0, 1. This will be number 3. Right. Then we're gonna go back here and back here. Oh, we got nothing here technically. Oh shit, I didn't even think about that. Okay, we're gonna go over here because we could technically add 0, right? I didn't think we started empty string. We'd either add 1 or 0 because technically, if I is empty, I is empty, so we can add 0. I didn't even think about that. So then we're gonna go back here. We're gonna do 0, 1, right? 0, 1. We can't add 2 zeros, so that's fine. Then here we're gonna go 0, 1, 1, right? That's 4. And then the other one here would be, sorry. We're gonna do 0, 1, 1. Then we come back here, obviously we can't add an extra 0, so we're done. So therefore, that's how we'd finish, right? 1, 1, 1, 1, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0. Wait, hang on. Oh, yeah, sorry. If not I minus 1 does not equal 0. Oh, shit, we already did that. So yeah, we can add a 0 here. Whoops, my bad. This is meant to be a 0. That's an interesting way to solve the problem. Like, see, I went the other way. I didn't really think about it like that. But I guess it's just the way you got to think about these problems is really the giveaway. But yeah. Alright, that was good. We did some backtracking problem, so I'm happy with that. We're gonna call it there. I will see you guys tomorrow. Thank you for watching.